So welcome to the last session of the tutorial. And here we are going to cover the voltage margins on FPGAs and how we can optimize applications for it. I will be starting with the motivation. My name is Osman Ünsal, and then my colleague Behzat Salami will continue with the rest of the session. Next slide. And so we start with the motivation on FPGA undervolting. And next slide. FPGAs are used very widely today on all levels of the software stack, from telecommunication to computing. Especially, they have been getting more popular in the data center side, and even more recently on the high performance computing side. So we are seeing a resurgence of FPGA use across many different domains. Next slide. Why is that so? Why are FPGAs becoming more popular? So because they address a couple of challenges in emerging applications. The first is for mobile applications, the stability of the power source, where the power is either battery or energy harvesting based, is an issue. So therefore, we need low power per operation computing fabrics. Another bottleneck that we have is the data movement bottleneck for big data scenarios, where we need to process close to data. We need fabrics that do the processing close to data. And last but not least, both the architecture and applications are evolving over time, which necessitates a reconfigurable system, unlike application-specific chips that are not reconfigurable or adaptable. And therefore, FPGAs has a good point on hardware acceleration between ASICs and the CPU GPUs. They have better power efficiency than CPU GPUs. However, compared to the ASICs, although they have more flexibility, they are still not sufficiently power efficient compared to ASICs. And we are going to address this issue through undervolting. So as was explained before in the other sessions, we are going to go below the nominal voltage levels, keep the frequency at the same point for power efficiency, but then that comes with a reliability cost. And here we are going to try to balance, optimize reliability against power efficiency. As a use case, we are going to look at neural network applications. Next slide, please. And at this point, my colleague Behzat will take on. Thank you.
Okay, thanks, Osman, for the motivation that behind the FPGA undervolting, and thanks everyone for attending to the last part of this tutorial. I'll be continuing with a very brief background about FPGA. Most probably you are all familiar with the FPGA. However, it would be nice to make sure that we are all on the same page. So FPGAs, they have very heterogeneous architecture with massively parallel components. They are distributed over the chip and clearly reconfigurable components. So we have several types of units, components like lookup tables, SRAM block, DSPs, and many other things. Even in more modern architectures, the way that the FPGAs are connected to the off-chip memory, it is different. So as you can see, for example, in this picture, the FPGA is connected to the stacks of the DRAM, which is basically HBM, through silicon interposer. Basically, so this architecture is representing a near data processing approach, which FPGA is and DRAM chips are on the same package, basically, not on the same die, but on the same package. So we have closer contact to DRAM chips through the silicon interposer. So what we do in terms of undervolting basically is realizing the most important components of this architecture, FPGA architecture, that they're consuming the power consumption, which in this case includes lookup tables and CLBs, on-chip memories, and HBMs. So what I'm going to present is more detail about power, specifically about power and reliability trade-off through undervolting for these three components. Before going to detail of each one of them, I would like to discuss a little bit here the common behavior that we observe for these three components in terms of the supply voltage under scaling. So this behavior that I'm showing here, of course, is without any number because the numbers might be different. Actually, they are different for different components, but the general behavior is here for all the components. So when we start reducing the voltage from the nominal level, which it is set by manufacturer basically, so we constantly achieving the power efficiency improvement until the system is crashed basically. But before that, we have two regions. The first one is the voltage margin, which already actually mentioned in the previous talks as well. So in this area, we are not losing any kind of reliability, either in lookup tables or SRAMs in HBMs. But after some points, after that we are undervolting below the let's say the minimum safe voltage or VMIN, the reliability starts to degrade actually significantly, and actually we are facing with the reliability collapsing, which this reliability can be translated for example, bit flip rates in memories, in SRAMs or HBMs, or it can be translated as for example, accuracy loss in neural networks that if there's a machine learning application running on the FPGA. So in short, this is the general behavior for all the components that we observed. And next, I'm going to go through each one of those components, those three components one by one, and discuss the results in more detail, and discuss this behavior and explore this behavior in more detail. So as I mentioned, this is the common behavior for all the FPGA components. So first, I would like to go through internal components of FPGA, which means basically mostly lookup table, but it can include routing resources as well. So for this part, we have evaluated the convolutional neural network, which it is actually shown here, how we implemented it. Yeah, I'm sure that you are familiar with the convolutional neural networks. They are very good. They have shown very good efficiency for image classification tasks. They are composed of several different layers like max pooling, convolution, etc. So we have developed it into FPGA. We applied also some application level optimization like quantization and pruning, and we have analyzed actually its interaction with supply voltage under scaling. So we have tested this for Zinc Ultra Scale Plus FPGA, actually three identical samples of this FPGA. And this is basically what we have observed in terms of result we achieved in result. So similar to the actually the general behavior that I have shown by undervolting from the nominal level, which in this for FPGA which in this case is 815 millivolt, we achieve more than 3 times power saving in total. But the first part is without any cost because it is the margin, but the rest has the cost. And this is, as you can see, it is achievable for all the benchmarks that we have tested. They are the most popular benchmarks, basically. So the second part is with the cost of accuracy loss, which in this case actually is the image classification rate, basically correct image classification rate, image classification accuracy. Sorry. So as you can see, this is the cost. This is showing the cost. You see that after this voltage margin, the accuracy of the neural network is dropping significantly, basically, for all of the benchmarks that we have evaluated. So this error collapse, actually accuracy collapse, has some variation, two types of variation, I would say. First is the variation among the workloads that, as you can see here, so it is happening with different variation. For example, for this one, for AlexNet, it is in 580, or for this one, it is in 500. It's a bit earlier, basically, so it's happening early. So we have this kind of workload variation. In addition to the workload variation, we have also a chip variation as well. So we have evaluated it for three actually identical FPGA examples, and as you can see, this dot is basically on showing the variation basically for different FPGA. But despite of this variation, so we see that this collapsing in the accuracy, which is the cost of the power that we are saving here, it's actually observable for all the workloads for all the FPGA. So next, I'm going to talk how we can actually control and prevent this kind of error collapsing, which for this one we have evaluated frequency under scaling. So meaning that at the meantime that we are reducing the supply voltage, we can also reduce the frequency. In the previous slides that I have shown, so the frequency was set to the maximum operating frequency, which was 333 megahertz. For this case, while that we are reducing the voltage, we are also reducing the frequency. By this way, basically, we are preventing the accuracy loss, because we are preventing the error that is happening. As you can imagine, reducing voltage, it is basically increasing the delay, and by actually reducing the frequency, also we somehow adjust our speed with the real delay that is available on the transistors. So basically, what's happening here is that we are preventing any kind of error, so we do not really have this collapse in the accuracy of neural networks. But as the cost, what we are paying is actually the performance loss. As you can see here, you can imagine that by reducing the frequency, we are actually increasing the execution time. So this means that the performance will drop. So as you can see, in this case, it is 30% drop in the performance. We comparing let's say the minimum safe voltage level and the minimum voltage that we can actually reduce, because we are reducing the frequency from 300 to 200. But what we are achieving actually is power, basically. As you can see, so since we are both reducing voltage and reducing the frequency, it is expected that we can get too much power saving, which it is in the case is 44% of power saving. So, but clearly, so the performance is not good. So depending on which parameters we want to optimize, we can go through voltage and frequency underscaling, or we can just go through voltage underscaling without downscaling the frequency. This is also related to the accuracy of the neural network that we are expecting, basically. If we do not want to lose any accuracy, it is actually necessary to go this kind of techniques. But if we can tolerate some levels of accuracy loss in our application, maybe we can even go better, we can even go better, we can achieve better power through even if we lose some levels of accuracy. So, so this was the fault mitigation technique that we have evaluated. Actually, sorry for this. Okay. We have done several other analyses and improvements in the paper that I would like to refer for there. And I will go to the next part, next components that we have evaluated, which is FPGA SRAMs. So, so SRAMs are organized in this way for FPGAs. They are organized in the context of blocks of SRAMs, each one with the size of usually 16 kilobit or sometimes 18 kilobit. So they are distributed over the chip, as you can see here. This little blue boxes, they are like 16 kilobit of the SRAMs. There are thousands of them in the actually modern FPGA, so totally it goes to few megabytes basically at some cases. So we have implemented a very simple, straightforward methodology to measuring and to evaluating undervolting in terms of the power and reliability trade-off for these blocks. So here reliability is translated basically the number of the errors that we observe in different cells of different block RAMs. So here basically is the result that we have achieved. So similar to the previous components that I explained, so we saw a very large voltage margin, which we are eliminating that basically is resulting to too much power saving. By the way, the FPGAs that we have tested, as you can see here, so the nominal voltage for all of them is 1 volt, because the technology is a bit older than the previous board that we have tested, we have evaluated. Sorry, but further undervolting below this voltage margin, we observe that the power continuously is reducing, but there are some bit flips that are observable in different locations of the block RAMs. As you can see here, the rate of them is exponentially increasing basically for all the boards actually. And finally, the system stops operating. So there is a slight variation among the different minimum safe voltage for different FPGA and the point that it stops operating FPGAs. But the most important and most significant variation, I would say, it is related to the bit flip rate for different FPGA. As you can see here, for example, there is even 10-time difference between this FPGA and this FPGA. So, which I believe that it is because of the process variation or maybe aging or even maybe some architectural differences, basically. And as another example, we have tested two identical FPGA, which architecturally they are exactly identical, basically. And again, we observe some differences. So as you can see here, the behavior here is 3-4 times worse than in terms of reliability this FPGA. So process variation is probably very important in terms of observing this kind of variation. So next, I'm going to go a little bit more details to understand this reliability behavior a bit more detail. So actually, we already see two behavior here. First is the exponentially increasing the rate of the faults by further undervolting, and the other one is variation. But there are more interesting behavior. That next I'm going to talk about a few of them. The first behavior is actually the non-uniform distribution of the faults. So if you remember, I discussed that the block RAMs are distributed. There are many of them. They are distributed everywhere on the chip. But the errors that we observe, total errors, they are not uniformly distributed for all the block RAMs. So what we observe is that this distribution is completely non-uniform. And for example, there are a few percentage of the memories, like in this case 1.8% of them, which are experiencing the biggest part of the actually errors, which 86% of the errors are experienced only in 2% of the block RAMs. And there are even some block RAMs that they never experience faults, basically. So this is a very good point because this can be used to actually smart mapping of the data to different SRAM blocks, because we can decide if there's a, let's say, critical data, we can somehow locate it here, or if there's less critical data, there's like normal data, we can try to locate them here. So this observation can be a source of a very good and optimal, efficient fault mitigation through basically smart data mapping, I would say. So there are other behaviors that I would like to mention. The one I'm discussing in this slide is called fault inclusion property. So this describes that if there's any fault at some locations at a certain voltage level, those faults are still there, even if we continue reducing the supply voltage, as you can see here. So this voltage is less than this one, and we still have those errors, and we have clearly some other errors in other places. And the same things here also. We have the same errors and continuously adding more errors with further undervolting. This is showing a little bit more quantitatively, as you can see. We have some errors in this case. So actually, this doesn't show the location, but the location is also confirmed. So the errors are it stays in the lower voltage level, but there are some additional errors, etc., and it's going up. And by the way, this is a logarithmic scale, so it is exponentially growing. So this is also a very good observation for some fault mitigation techniques, and there are some works that they took this and they have implemented. For example, for CPU caches, they have implemented this for finding the minimum safe voltage that they can actually at runtime they can reduce it, and we actually confirmed it for FPGA block RAMs as well, and we are actually trying to right now exploit it for some fault mitigation techniques at this point. I would like to mention the variation again. We already saw some result about the two identical samples of the that totally different fault rate, basically for two identical FPGAs, as you can see here, the same voltage, more or less similar voltage, the fault rate is completely higher, 3-4 times higher for this FPGA compared to this one. In addition to that, here I would like to mention highlight the location of the error. So there are not only the rate of the faults are completely different, the location of the faults could also be completely different. As you can see here, this is showing the fault map, I would say. So there are some block RAMs that which they are completely high vulnerable, let's say in this case, for example, here, but they are completely low vulnerable, actually the identical location in the other FPGA. So not only the rate of the faults, also the location of the faults are also completely different, again, because of the most probably the process variation, die-to-die variation impact. So the message of this slide is that any kind of fault mitigation technique that is trying to exploit this kind of maps to basically to minimize the effect of these errors, it should be chip dependent, because the behavior is completely independent between for different chips, even if the chips are identical from the same family. So we have considered actually this when we were designing some efficient mitigation techniques. But today in this presentation, I'm going to talk about a common error mitigation technique for SRAM, which is based on built-in ECC. So it is pretty straightforward, because the SRAM blocks that are available in the FPGA, they are already equipped with this built-in ECC capability, and we have evaluated it how to understand how it can be useful to mitigate the errors of undervolting errors. And this is more or less what the result that we have observed, and that was pretty interesting, that we observed that most of the errors that is through undervolting or repair in the on the SRAMs, they are disappeared and they are recovered basically when ECC is enabled. So considering the point that the ECC has the type of sected single error correction and double error detection, we did a characterization, and we observed that the most of the errors, undervolting errors, they have the type of single bit, which can be easily corrected basically by this ECC, because ECC is actually designed to correct these errors. So the number is shown here. So more than 90% of the errors has the type of single bit, and there are a few percentage that they are double bit or multiple bit. So ECC is pretty useful basically for detecting and for correcting, especially undervolting errors in FPGA SRAMs. So we have applied it for DNNs, which I already showed the methodology, and as expected basically somehow. So the error rate, the accuracy, actually in this case it is classification error. So the classification error of the NOR network is reduced significantly to almost zero, negligible, or maybe negligible error rate basically through just enabling ECC. And also maybe it is good to mention that the cost of this built-in ECC that is already available is not that high, which I believe because the ECC implementation in the FPGA, it is based on some efficient ASIC unit. So it does not really incur too much power or performance overhead. However, there was a little discussion about that in terms of the overhead, which we already discussed in the papers. So I would like to refer there for more discussion about the ECC. And finally, I am going to talk about undervolting in high bandwidth memory as the last components that we have studied so far. HBMs, you remember this figure? So it is showing a real, basically FPGA-based HBM that we have tested from Xilinx. So there is a little bit more details as shown here. So we have different chunks of the memory for each HBM stacks that is available. So we have 2 stacks, by the way, for this FPGA. So there are 16 chunks of the memory, each one 256 megabyte. So each of these memories are connected to the FPGAs through some pseudo channels, which means that totally we have 16 pseudo channels. There are also some switches in the middle, which provide some flexibility. So clearly the benefits that this system provides is the bandwidth that we can have by exploiting them all in parallel, basically. And what we are gonna do through undervolting is improving the power efficiency of the memory chunks that is basically available for all the bandwidth ratios, independent of how many memory channels and how many of these memory chunks we utilize, basically. So this is something is achievable through undervolting, and we show it here basically. So as you see here, by undervolting from the nominal level, which it is 1.2 in this case, for all the bandwidth ratios, we achieve power saving more or less with the same rate, basically. However, until some points, this voltage reduction, voltage decreasing does not have any cost in terms of the bit flips. But after some point, we observe some errors in different HBM stacks and in the different locations in different chunks of data, which is shown here in terms of the rate of the faults. As you see here, similar to the SRAMs that actually we had in the previous part, as you see, there is an exponentially increasing rate of the faults. However, there are some variation in terms of the data pattern and in terms of the stacks and in terms of the basically the channels that we have. We show all this variation here, basically three types of the variation that I mentioned. First is the variation related to the HBM stack. So we have two stacks, as you see here, HBM0 and HBM1. The other variation this figure is showing is the data pattern, which is in this case 0 to 1 bit flips, this one, and 1 to 0 bit flip is the below one. And finally, is already observable the variation between the pseudo channels, basically, as you see here. So we have 16 pseudo channel per stack, and they're showing some variation, basically. So this variation is already there, and we believe that this would be very interesting if we show this potential for application, basically, because application can have different types of the data, and basically based on the resilience level of different types of the data for different applications, we can try to find an intelligent mapping for those data into this application, which in this case, actually, I'm going to show a little bit more analysis. This is basically a translation of the previous slide. It is showing the tolerable fault rate, which application can go each of this category. This is showing the supply voltage level. And these numbers here, they are showing the number of the pseudo channels that we can exploit, basically. For instance, if our application has 0% is not at all tolerable for any fault rate, but it requires all the memory. It requires all the memory, meaning 32 pseudo channel of the memory. So this means that the voltage that we can reduce is 0.98 volt. But if we have another application, which similar to the previous one, requires all the memory, 32 channel of the memory, but it can tolerate 50% of the error, this means that we can basically reduce the voltage to 40 millivolt lower than the previous one. And even we can go further. If we have an application that similar to application 2 can tolerate 50% of the fault, and it only requires a single channel of the memory, which means 256 megabyte of the memory, this means that we can go through 0.80 millivolt, which means 100 millivolt less than actually the previous application. So this is basically meaning that we can trade off. We can trade off the voltage, which is directly translated to the power, with the tolerable fault rate of that application, and also with the required memory size of that application. So I'd like to summarize the presentation today. So we have discussed the requirement of the emerging application for FPGAs because of the unique features that FPGA have, especially because of their flexibility, better flexibility than ASICs, and also better throughput than GPUs. However, FPGA power consumption is a problem, is a serious concern, and we tackle this problem through a hardware level technique undervolting. So we have evaluated these techniques for real FPGA. We realized large voltage margin. We have evaluated power and reliability, trade-off, error characterization, mitigation, temperature, and frequency underscaling, and many different things for several components of the FPGA, basically. And we evaluated it for machine learning application. We achieved more than 3 times power saving on average, which includes by eliminating the voltage margin, and also by further undervolting below the voltage margin, which has the cost of the reliability. And also we did a lot of analysis for the reliability, which I have shown some of them in this presentation. But there are even more that can be found in our paper. So you remember this figure. We did more analysis for different types of FPGA in terms of margin, different technology nodes, for example. We analyzed the behavior below this margin, even more detail in terms of the characterizations for HBM, for SRAMs, and for the lookup tables. We analyze variability, for example, for different workloads, not only machine learning, other workloads, for environmental temperature, frequency, etc. We propose several mitigation techniques that I discussed about ECC today for SRAMs, but there are more mitigation techniques that we have proposed and analyzed. We are working now on optimizing the voltage architecture for real FPGA. We have realized that this architecture can be improved, and now we are trying to make it more efficient in terms of distribution of the voltage, in terms of better power and performance trade-off, etc. We are working now integration of this technique with software, which meaning that the application developer can easily exploit it for implementation inside their program. And finally, we are trying to emulate the results into the simulation tools like for GPU and for CPU as well, which would be very useful. Basically, for example, the CPU caches, they have the same technology like FPGA block RAM. So maybe the real results that we have observed and we obtain in this study can be useful for that kind of studies as well. So with this, I would like to thanks for your attention and thanks for attending to this talk. And I'll be happy actually to take your any comment or question offline, or if you have any points for now, I'll be happy also to take it now. Thanks so much.